Welcome to part 6 of the CipherVibe Cloud Security Capabilities series. This episode explains AI security, why it matters, how the capability works, which mistakes weaken it, and how to build it in a measurable way. AI security addresses the risks created when models interpret untrusted content, generate decisions, retrieve private data, and invoke powerful tools. A complete program covers traditional application security plus model behavior, data governance, prompt boundaries, agent authorization, and monitoring. The key idea is that a security capability is more than a product feature or a collection of alerts. It combines people, process, technology, decision rights, evidence, and continuous improvement. We will examine its architecture, operating workflow, failure modes, defensive controls, implementation roadmap, and useful metrics. Coverage is not the same as effectiveness. A dashboard can show thousands of checks while the capability still fails because evidence is stale, ownership is missing, or remediation is never verified. The business outcome should be explicit. Teams need to know which loss scenarios the capability reduces, which systems are in scope, and which remaining risks require a conscious decision. To understand AI security, start with its architecture and vocabulary. The capability should create a traceable chain from source evidence to a security decision and then to an accountable action. First, prompt injection attempts to make untrusted instructions override the application's intended policy or manipulate tool use. Second, retrieval-augmented generation adds document ingestion, embeddings, vector search, authorization filtering, provenance, and response grounding. Third, AI agents combine models with memory, planning, credentials, tools, and external actions, increasing both capability and blast radius. Fourth, model supply chains include training data, fine-tunes, adapters, weights, evaluation sets, libraries, registries, and hosting services. These concepts need shared identity, timestamps, provenance, ownership, and access control. Every summarized risk should link back to its source evidence and disclose missing information. A sound architecture separates collection, normalization, analysis, policy, workflow, and presentation. Teams can then test freshness, identity resolution, policy results, owner routing, and closure independently. Design for degraded conditions. Providers impose rate limits, schemas change, credentials expire, and events arrive late. A professional capability reports uncertainty and health instead of presenting incomplete information as fact. Trust boundaries deserve equal attention. Identify where data crosses accounts, tenants, regions, vendors, privilege levels, and administrative domains, then apply authentication, authorization, validation, encryption, and audit controls at those boundaries. A useful operating model for AI security follows a repeatable evidence lifecycle. First, inventory AI use cases, models, data sources, tools, decision authority, external exposure, and accountable business owners. Second, threat model data flow from user input through retrieval, model inference, tool invocation, storage, and downstream action. Third, define security evaluations for prompt injection, data leakage, harmful output, authorization bypass, and unsafe tool combinations. Fourth, constrain tools with deterministic policy enforcement, scoped identities, validation, approval, rate limits, and transaction boundaries. Fifth, monitor prompts, retrieval, outputs, tool calls, policy decisions, abuse signals, and user feedback with privacy-aware retention. The workflow does not end when a ticket closes or an API returns success. Security closure requires fresh evidence showing that the risky condition is gone and does not immediately recur. Ownership should be established before urgent findings arrive using service catalogs, business applications, on-call schedules, and escalation paths. Prioritization should explain the influence of exploitation, reachability, privilege, data, business criticality, compensating controls, and confidence. Repeated findings should drive changes to secure templates, defaults, libraries, identity patterns, and architecture standards. Define escalation points for missing owners, disputed priority, failed changes, and evidence that suggests active compromise. Those conditions should move into incident or risk governance rather than remaining indefinitely in a routine queue. The fastest way to evaluate AI security is to study how the capability can fail. First, treating the model as the authorization layer allows persuasive text to influence access decisions. Second, retrieval systems leak data when document-level permissions are not enforced at query time. Third, agents can chain individually acceptable tools into a dangerous sequence with unintended side effects. Fourth, sensitive prompts and outputs may be retained by vendors, logs, analytics, or support workflows. Fifth, benchmark scores can create false confidence when production tools, data, and attack paths differ from the test. These failures share a pattern. A local measure looks successful while the full outcome is weak. A connector, scanner, or repair can report success while coverage, exploitability, or recurrence remains unresolved. Measure whether the program improves important coverage, shortens exposure time, removes attack paths, and prevents recurrence, not how many alerts it produces. Exceptions need a reason, owner, compensating controls, approval, and expiry. Automation should reflect confidence, reversibility, blast radius, and business impact. Test both through controlled failure exercises. Correlate weaknesses instead of reviewing them separately. A moderate configuration issue, broad identity grant, exposed service, and sensitive data store may combine into a severe path even when no individual alert looks critical. A dependable AI security program uses defense in depth. No single scanner, policy, gateway, or agent should be expected to carry the entire outcome. First, keep authorization and business rules outside the model in deterministic, testable enforcement services. Second, separate instructions from untrusted data, label provenance, limit context, and treat retrieved content as potentially hostile. Third, use allow-listed tools, typed parameters, output validation, least privilege identities, and approval for consequential actions. Fourth, perform model and application evaluations before release and continuously after changes to prompts, tools, data, or providers. Fifth, define privacy, retention, vendor, incident response, and human oversight requirements for every AI use case. Control design should include preventive, detective, responsive, and recovery layers. Together, they establish safe defaults, identify drift, govern containment, and restore service. Least privilege applies to connectors, agents, orchestration identities, data stores, and administrators. Scope, separate, monitor, rotate, and test their access. Every control needs an owner and test strategy. Validate it with representative assets, negative cases, simulated attacks, provider failures, and rollback exercises. Integrate controls with engineering through clear pull requests, owner routing, reusable fixes, documented standards, and fast feedback. Preserve an evidence trail from detection through decision, approval, change, and verification. That lineage supports investigations, audits, lessons learned, and fair performance measurement without forcing teams to reconstruct history from separate systems. A practical implementation roadmap for AI security should build trust before scale. First, create an AI system inventory and classify use cases by data sensitivity and action authority. Second, secure one representative application end-to-end, including retrieval and tool boundaries. Third, build reusable evaluation suites and policy enforcement components. Fourth, add runtime monitoring, red team exercises, change management, and incident playbooks. Fifth, scale governance using risk tiers while preserving a fast-approved path for low-risk experimentation. The roadmap is incremental because a focused production scope lets teams validate evidence, ownership, workflow, and control safety before scaling. Useful measures include AI use case inventory coverage, evaluation pass rate, unauthorized tool call rate, sensitive data leakage rate, and high-risk action approval rate. Give every metric a precise definition, data source, owner, and known limitation. Pair lagging indicators such as exposure age with leading indicators such as coverage, control health, exception expiry, and secure template adoption. Maturity means the organization can discover important risk, explain it, assign it, act safely, verify the result, and learn from recurrence. Review the roadmap quarterly. Changes in architecture, threat activity, regulation, business strategy, and provider services can alter both priorities and assumptions. Retire metrics and controls that no longer guide useful decisions. For more cybersecurity market intelligence, research, and educational briefings, visit CipherVibe.com. CipherVibe is operated by Cloudsectech LLC. This video is general education, not legal, compliance, financial, or incident response advice. Never access or test systems without explicit written authorization.